All You Need in 2017, and it was a groundbreaking achievement for the field of natural language processing and text modeling and AI. Um, and just a quick recap on our previous workshop. So when you have a sentence that is tokenized, for reference, this is how does ChatGPT work? If you weren't here in the previous workshop, um, we just converted from this discrete form in tokens into this multi-dimensional continuous form. And we also changed the notation a little bit. The reason for that change is because of the to address the paper that we'll be going over. So for a lot of these things, we'll be also looking at attention is all you need. This way, I'm hoping to make you guys more comfortable with reading actual literature, and it's not that scary as it seems. But so we take an input, we tokenize it, and then we embed it into this dimensional space. D represents the number of embedding dimensions, and L represents the length of our sequence. Um, and from now on, we are going to refer to this input that we are giving as an embedding vector E. And embedding vector E is going to be of real numbers in this dimensional space. So B is going to be the batch because these models are made so they can work with batches. And then D and L are going to represent the embedding dimension and then the length dimension. Now I'm going to quickly go over the paper actually, and then we're gonna kind of summarize it with the slides after this one. Okay. Okay, so this is the paper. Attention is all you need. Now, if reading papers is something that you are interested in and you want to do more of, the software I'm using right now is called Zotero. Zotero is this software made for scientific literature. It allows you to group the papers you're reading into categories, directories, and also allows you to comment things, highlight things, and keep your literature structured. Also, it's a great citation tool for references. So if you're writing a paper of your own, you are able to easily take the papers that you put in a directory and then create a reference list out of it. It's a great tool. But um, yeah, let's get started. So we're gonna slowly go over this, and we're not gonna obviously read. There's a whole bunch of stuff that we don't need to read, such as the introduction. Um, but for reference, here, also, by the way, can you guys read? Can you see the text clearly? Yeah, okay. So, for example, here it mentions recurrent neural networks. For reference, I think I mentioned it in the first workshop as well. But the reason it's mentioning recurrent neural networks is because for the longest time, they were the golden standard of um, modeling sequences. So whether it be time series or text, recurrent neural networks were the standard. They were suffering from their own problems, um, and this paper addresses those by developing a whole new architecture. And for, you could say even today it replaced it. There has been a revival in recurrent neural networks used in sequential modeling, but for the most part, transformers achieved a golden standard. And so this line is very important. So with introduction, what you will often find is that it's really the last few paragraphs that are most important, because the first paragraphs in an introduction usually outline the general topic that the paper is covering, maybe prior work, the challenges, the drawbacks. But in the last paragraph of the introduction, you will usually find what is the novelty that the paper you're reading is presenting. And we can see that in our case, it says that it's a model architecture. It's eschewing a recurrence, and instead it relies on an attention mechanism to draw global dependencies between input and output. Um, and we'll see how they do that. Then this is the background, but we can skip it because we are going to go straight down to the model architecture. Now here they also mentioned the encoder-decoder structure. I think I mentioned that large language models use mostly the decoder structure. Um, and so that's what we are going to be focusing on, but you can still read this paper as is, even though they present transformer as a encoder decoder. Um, and also, as mentioned in the previous workshop, at each step the model is autoregressive, which means that it's continually generating outputs. So it doesn't generate the whole output at once, but you kind of have to generate the next word or token and then feed it back into the input and do so until it decides that it is done. Um, and we don't need to go over these specifics because they just specify like the parameters of the transformer architecture they use for their benchmarks. But in reality, all you need to understand is what is going on here. Um, and so on in the first workshop, the part one, we covered the input embedding part, and we also covered the positional encoding, and we also covered the autoregressive part of this architecture. Today, we're mostly going to be focusing on this part as well, mostly on this part. Um, and this is the main topic of today will be the multi-head attention, or particularly in our case, masked multi-head attention. We're not going to dive too deep into add and norm. I will cover it, but normalization is something that we're going to cover in the next few workshops. Um, but let's get to attention and what it is. So if we see here, with our attention, how do we figure out what is going on and what is going into our network? So here it says that attention function can be described as mapping a query and a set of key value pairs to an output where the key query keys, values, and output are all vectors. And in our case, um, at the beginning, they're all created by the same embedding vector. Um, and what they do is they just take those vectors, they create them by multiplying them by some parameter matrices, and then they use attention on it. And if we go up, here it says, in addition to the two sublayers of the decoder, okay, so this is the decoder. We also modify, okay. Um, and I think my slides are gonna be a bit better in explaining all this. Um, but really, we want to see that the main key takeaways for why we divide this by dk is because for numerical stability, um, and that is covered here. We suspect that for large values of dk, the dot product grows large in magnitude, pushing the softmax function into regions where it has extremely small gradients. And so you can just understand that in our softmax function, this parameter here is just going to be for numerical stability. But how do we get this q and how do we get this k, and what are they? What purpose do they serve, and um, what is the value? So they could have done a bit of this paper does require some prior knowledge, but it's really rather simple once you simplify it all. So let's begin with the key. So key is created by us taking some embedding, transposing it. And the reason I transposed it is because I'm using our notation and I don't want to change things around, but they use our notation transposed as the embedding. So for transformer, the original notation, they use length times the dimension. In our case, we use dimension times length because I think it's more intuitive to visualize it, right? Because you kind of think of as length being the column and the dimension being like the rows, because it is the more familiar type of data you used to be working with. And the way we create our key is we take the embedding and we multiply it by some parameter matrix W. And parameter matrix W it's going to have a matrix for both the key, both the query, and both the value. They're going to be separate weight matrices. So they're going to be doing separate things. And the shape of that matrix is going to be um, the dimension of our model times the k. And so what is k? K is going to be the dimension of our model divided by number of heads. And I'm hoping that as I go through this, you will maybe with some intuition figure out like why are we doing this, um, and why isn't this the shape of our full dimension? So why has it been shrunk to just this smaller dimensional space? But so that is our k, and if we look at our query, um, the same thing applies except I'm missing the transpose there, but we use a separate matrix Q, we multiply the embedding by it, and then we get the query. And then same thing for value. But what do they do? I mean, this is pretty straightforward, but we still don't know the purpose of all of this. At least with like MLPs, when we see those weight matrices, we could understand that they're kind of reshaping the data in this different dimensional space. But what is the purpose here? And so first, before we move on, we just gotta make sure we have our dimensions in check. So we know that what are we multiplying and the shape of everything, because I think it is very important to know the all of inner workings of a structure. So these are our three matrices going into the attention block. So um, and then this is what we have seen. This is the attention score. It is the softmax of once we put all of this in. So now we are just adjusted to our notation. So we took their notation in one of the first slides, and now we're more familiar with, I mean, really the biggest change is here. So first, we got to cover softmax. And why is it used, and what purpose does it serve in attention? So softmax is a nonlinear function because on its own, when you multiply query and a key, that is a purely linear operation, right? So we cannot ever expect this product on its own, query times the key, it can never be nonlinear, right? And so if in our transformers, if they're not linear or nonlinear, we can't expect them to model complicated relationships, which text is a very complicated structure. Um, and so you can kind of think of it this being similar to ReLU, except it serves a different purpose, and you'll see why. But I also added another term here, which you haven't seen so far, which is the separator function. So the reason I call it the separator function is because it kind of separates the values of the dot product similarity that it's calculating in the attention layer. And this kind of stems from what will be covered in part 3, used in some more dynamical models that are, you'll see, very similar to attention. But softmax is a really simple function, so we just go over all of our inputs, and then we just kind of calculate its ratio using the exponentials. And this ensures that depending on over which dimension you want to apply softmax, this will ensure that all of the values, say in the columns, they all add up to 1. So that they're probabilities, and that we can have that our tension score is the probabilities of what though? Well, so this. So when we have an input, how does ChatGPT work? And the WS here is white space. The reason I put WS is because PowerPoint didn't really let me do this in a nice way, just to have like a purple block. So I just had to put this in. So if you remember, so we just use the same embedding for query and the key. And so you can think of this as being the query, this is the key, and then now we're just trying to figure out um, for a given query, what is the appropriate key. So for example, we can think of chat being our query. So what is chat? Well, we're looking for chat GPT, right? So where GPT would be the most appropriate query for our, or sorry, GPT would be the most appropriate key for a given query that is chat. And this is the attention score matrix. Now, we have this triangle here of negative infinities. Can anybody tell me why is that? Extra points on the leaderboard if you answer a question, even if it's wrong.
It has something to do like in linear algebra when like the top part of the triangle is all like zero values multiplied diagonally.
No. So the keyword here is causal. So what do we have to ensure when our model is modeling text? What do we have to make sure of? If this didn't exist, right, it could model this, right? So it could model um, this point right here. But what is wrong with modeling that point? Yeah. Yeah, very close, yes. But that's pretty much it. Like we can't model, say, for example, the relationship between how that's at the first position right here and then this right there, because then our model would kind of learn these relationships of the last word in a sentence with the first one when it only produced the first two words. So you can think of it as like a future bias. If you ever played around with um, stock trader bots, if you have backtracking strategies or backtesting, you can't make your algorithm know the future because that is called the future bias. So same thing here, right? So you can't have a model know the relationship between these two because it didn't know what it output in between at all, right? And so maybe in training it would work well and it would model it, but then in auto-regressive inference mode, it wouldn't know what to do, right? Because it just didn't generate those tokens yet. And but why negative infinity? So why are we using negative infinity here to ensure that there's no future bias? Um, if we go back, we're using softmax, right? In our attention score matrix. So if we're using softmax, um, oh, actually, I'm going the wrong direction. Oh, okay, so we're using softmax. What will happen with these values when we apply negative infinity? Yeah, exactly. We want them to be to zero. And so because we don't know the overall magnitude of possible scores between the two, because some of them may be very big. Because remember, this is, should have mentioned that this is before softmax. So afterwards we apply softmax, but there's been a, I think I lost a slide. Anyways, so this is before softmax. And you can think of that any of these values, like for example here, it could be a very big number, right? And so it's going to have a very big contribution to its value after softmax. So what we need to ensure is that this value is so small and so negative that it is going to be cut down to zero, right? So that's why we use negative infinity, so that all of those values after we apply the softmax on this will be set to zero. And then this is just another term that you should be familiar with, is that, for example, when we have this relationship right here, 0.4 between chat and GPT, we can say that GPT attests 0.4 to the query of chat. Um, and so that means that it has like a high score. High score between these two means the importance and a relationship between them. Um, and so the key takeaways from causal attention is that it is going to capture the structural relationship in the text. So it is going to look at things in what order they are. So um, remember, this is all produced in parallel, but in workshop number 1, you saw that we give positions to each of the embeddings in our sentence so that we know where they are. So that's why it's able to know um, the order relationship in our input, and also the rich contextual information of each and every single word and how do they relate to each other. Um, and then we enforce the sequential analysis, so we can't just have our model learn just the full spectrum of the text because it needs to do it in such a way that it's able to later generate it. And then we are just using a softmax as a nonlinearity separator function so that it can separate the smaller values that go towards 0 a lot more, and whereas the bigger values are going to go a lot more towards 1, and it's going to be nonlinear. Um, Before I move on to the value part and what does it do, are there questions? Okay, I'll take that as a no. Um, so the purpose of value is that it gives context on our input, right? Because it is great that we understand the structural relationship in our input, like how does each word relate to each other, the importance, and so on. But we also need to understand the context of our sentence. Like, in what context are those words? And I'm gonna do this with another example. So far we did an example of how does ChatGPT work, but for this one I'm gonna use a different example, mostly because it's kind of hard to visualize how does ChatGPT work because they're all very abstract terms. So we're gonna use something a lot more visual, and that is a bright yellow star is falling from the sky. Um, and so if you've already seen, we can do attention on our input where we kind of measure the importance of each word at every position with the other one at different positions in our attention matrix. But what is the context? And the context you can think of as, so first we're going to embed it, and each and every single word is going to have rich information about it. And that can look something like this. So these were all AI generated. I would just put in like a word, and then it would just generate an image. And so this is a abstract term for bright, an abstract term for yellow, star, falling, and then sky, or like this one. Um, but on their own, they don't mean much, right? So you take a look at every single one of those, and you're like, okay, cool. So I see a star, I see whatever the hell this is. Um, you see this, okay, yellow. But on their own, they don't mean much, and they're just a separate abstract term that doesn't have, I guess you could say, the utility that the richness of our text usually has, especially when given context. So you can take a value, putting that all together. So instead of just having the understanding of how does yellow relate to bright and how does it relate to star and so on and so forth, we want to know how does all of it relate together in aggregated form, and we get this. This is actually the one time that I was surprised by PowerPoint's designer. Did a cool job, I guess. But when you aggregate it all together, you get a bright yellow star falling from the sky. So now we have conceptual information about um, all of the words in our input. Um, and what I want you to take away from today is that attention directs our input. And what do I mean by that? So if you remember, when we have a certain input, right? It takes it and then predicts the next word, but it predicts the same size So the output is the same size as the input, right? So if you have 5 tokens, it's going to output 5 tokens, or it's going to be a lot more dimensional, but the shapes are going to be roughly the same. So what does that tell us? So let's go back to the paper. This is actually one thing that we can use. Um, so when we look at the architecture and what is it doing, um, if you see here, so we take our embedding, we take it, we encode it with position, and then I guess I can now actually just come over there. So we take our embedding, and then we put attention to it. But if you see, unlike the MLPs, where we take an input and then we propagate it through layers directly, and then it's completely changed, we actually keep the original embedding intact. And so what we do is we only update it after it has gone through this layer. So this is, you can think of like a residual connection where you have you clone a input, you propagate it through a certain amount of layers, and then you add it back onto its original self. And that is done for multiple reasons. It's very useful because the back propagation is a lot nicer. We can remove the effects of vanish and gradient when our network is too big. But here, I think it's a lot more important. Why do we do this? And it's a bit of a different reason. So you can think of as, so we repeat this for many times, right? And also we have the feed forward network, but we do the same thing with it, right? So we propagate it through the feed forward, and then we add that onto our original input that keeps changing. So as we go on through the layers, you can kind of think that we are slowly shifting our input towards the right gradually. And as more we go through these layers, the closer it is going to be towards the next probable token. And I think that's very nice intuition from them. And how can we deduce that? If you remember from the attention score, right? It's all probabilities, right? And those probabilities are going to be multiplying our context. And when they multiply our context, we can kind of think of that as we're enforcing value towards some direction over the others. So you can almost think of as our input is moving through a field. Um, and we keep doing that, and at each step we are going to be adding the attention and the feed forward back to our input, and we're going to slowly through the layers shift it until we get to well, again, until the end. But the idea is that through all those layers it is going to shift it from, say, um, how does ChatGPT work, and then it's going to shift it 1 token to the right, because that's how it was trained on over text. But it does it gradually, and it doesn't do it all at once. And to show you what I mean, I'll show a teaser for our next workshop. Um, and so this is, I guess, just what I reiterated or said, except on a slide. Um, and you can think of that as a field. Now, it may not be obvious quite yet, but we'll be going off over a very old architecture, Hopfield networks. Um, they are one of the oldest neural network models, or neuronal models, introduced by John Hopfield and this guy Artem Kirsanov. He has an amazing channel. He covers a lot of topics. He's a PhD student in the neuroscience department at NYU, but he loves to cover topics closely related to AI. But what you can think of is our text is just these patterns that are in this energy field down which we are descending. And it's really just this distribution that is obviously very simplified here because it's in 3D space, but you can think of is that our input is shifting through these basins, or what do we call it, tractors. So it's going from one place to another. So you can think of that when it's shifting to the right, it's kind of ascending up and then down. Now, I won't go too much into that. That will be part of our next workshop. Um, but I think it's a very cool way to think of attention, and it kind of demystifies it by a little bit. Um, and so, what about multi-head attention? So, I know this is a bit hectic. I'm sorry about that, but we kind of go now from the. Before I move on to the multi-head attention, are there any questions?
I actually have one question.
Yeah.
Maybe back on the paper. So like there were the boxes, and I think they had a label NX next to them. Does that mean it keeps like
Yep.
for a
Yep.
certain amount of time?
Yeah. So, uh, in this paper, they mentioned that they have 6 layers. So you can think of is that it's gonna do this, it's gonna do that, and then it is going to do this 6 times before it moves on to this. This is the output head, and the output head projects it into um, the length times the vocabulary size, so that we can get the probabilities of which word is the most probable, and then finally we apply the softmax. So first is going to project it into vocabulary size, and then you apply the softmax, so we know at each position, um, from all of vocabulary, which token is the most likely to be there. Yep. Any other questions? Okay. Um. Oh, that's not it. Okay. So what about multi-head attention? So what you can think of is that. So remember how we have our input that is the amount of words that we have in the input, and then it's the amount of dimensions of the embedding vector. So instead of putting that entire thing into one head of attention and then calculating it, which can be slow, what we do is we have multiple heads. And in our case, let's say we have 8. So those 8 heads, and if we consider that our embedding dimension is um, 512, each head is going to input 64 dimensional vector. And so what does it do is that each head is going to be kind of working on in the different, what should I call it? It's going to be working on the different dimensions in our embedding space. And so why is that good? Is because first of all, it's computationally efficient. Transformers are very parallelizable, so we can parallelize the hell out of them. Second, they allow to learn different tasks, and I actually have a visual example of from the research that I'm doing how it is able to capture different relationships in different heads, and then so that's all fine. But how do we go back? It's really simple. What we do is we concatenate from each of the head the output, and then we weight it by some other matrix. And let me show you in the paper how that's done. Um, okay. Oh, here we go. So this is multi-head. So it follows the same formula, right? And so what it does is we concatenate for each head and say we have 8 heads. So we're going to go over n amount of heads. And then we are going to multiply that concatenation by a projection matrix WO. Um, and for each head, we are going to have a separate matrix for both the query, the key, and the value, so that, as I mentioned, each head is going to specialize in a different task. Um, and so, what do I mean by that? Um, so, what do I mean is, for example, um, quiet warning. So, light mode is incoming because my plots were with the black font, so you wouldn't be able to see it. Okay, so I forgot to put the labels here, what is what. But if you can see, so we have two different heads here, and each of them is learning uh, a different thing. So it's focusing on different parts on my data. It's giving different importance to different inputs. So this has to do with the microbiome of the soil. I was structuring the data in a bit of a different way, and I found some very interesting insights, how sometimes it values very different philia over the other. But you can see that, for example, for head number 1, it is diagonal heavy, which is often found with attention heads in transformers. What that means is just giving importance to the structure of the inputs. So for example, here, I forgot which one that is, but it's giving very big importance to one of my embeddings. Whereas here, it is kind of capturing more of the global relationship between my inputs. So it's not so much giving kind of value in the diagonal. Also, one thing to note here is that I'm not using causal attention, so it is a bit different from what you would see with large language models. My data doesn't have auto-regressiveness, it's just pure data in, output out. So um, you probably wouldn't see anything up here. But in my case, you do because, um, as I've said, it's not causal. But if you can see, it's kind of like cloning itself uh, on the top half and the bottom half. Um, and yeah, this is our reference. I would highly recommend going over this paper in your own time. May that be your homework. To go over attention is all you need. Try to understand it better. We will also upload this video, but in reality, if you want to learn all of this, you got to do it yourself. These workshops are meant as an introduction to a topic, to pique your interest. To learn, you got to do it yourself. But if there's any questions, I think that concludes our second part of our advanced workshop. Yeah, all right, thank you.